In this video, we should see wave shapes in circuits, in which we are discussing in this video clipping circuits. So this is the first part of the clipping circuits video. So let us consider the clipping circuit, which is shown in figure here. So here we have a resistor. VR is a reference voltage and is a diode. And this Vin is a AC signal. It can be a sinusoidal waveform or it can be a triangle waveform, but it is a AC signal. So of amplitude certainly more than VR as well as the VD on of the diode. Now in this case we are assuming that the diode on voltage, the VD on is 0 volt, and to analyze this wave shaping circuit, so let us try to find out the equivalent circuit of this clipping circuit when diode is on and off. So in the first case, so let us consider the case of when this diode is on. If D is on, so it is now represented by a short circuit. The output voltage is nothing but the voltage at this point with respect to on, because this short will be 0 volt. So the question is, when does this condition is existing? So this condition exists when the input voltage is more than VR, meaning when the input voltage here is more than VR, it will overcome this reference voltage which is being placed here. So the diode will be forward biased only when the input voltage is more than VR, meaning this circuit will give an output voltage of 0 volt if the input voltage is greater than the VR. So VR is nothing but this reference voltage. So let us see how does the equivalent circuit looks like if the diode is off. Now this is the circuit. Now we are trying to represent this diode by open circuit. Now this is open circuit. This is the output voltage. Now if you write the KVL for this, writing the KVL for this and considering the positive for voltage rise, so V in minus of VR minus of V naught is equal to 0. And since there is no current flowing, so the drop across the resistor is 0. That's why we are not considered any I into R part. So from this expression, we can write what is the value of V naught, which is nothing but V in minus of VR. Now this will occur, or the diode will be off when the input voltage is less than or equal to VR. So let us see the transfer characteristics of this clipping circuit. Now this is the transfer characteristics. The dotted line is written indicating. So this is the dotted line reference line. So if the input and input is there in both x and y axis. Now as we can see here, we have marked one more reference line here corresponding to VR. You can see this dotted line is corresponding to VR. So why we have written this is because any input voltage, because x-axis represents the input voltage, any input voltage more than VR, you can see diode is on. Any voltage less than VR, diode is off. So this will going to show us what is the condition of diode corresponding to the input voltage with respect to VR. If the input voltage is more than VR, the diode is on. If it is less than VR, it is off. Now we know that from the expression, when the input voltage is more than VR, V naught is 0. So we are writing this as 0 voltage. So this is the corresponding output voltage. When the input voltage, when this Vin is less than VR, the output is Vin minus VR. So this is now Vin is now it is the value of Vin is VR here. So what is the corresponding output voltage? So output voltage when Vin is equal to VR is equal to, it is Vin minus VR. So if Vin itself is VR, that is assume that VR is 2 volts. If input is 2 volts, so 2 minus 2 is 0. So that's why the output voltage is 0. As we can see here, so this blue line, which is exactly in parallel with the input reference line, is having a difference of VR at each and every point. So this means that output is always less than the input by this reference voltage. So this reference voltage can be either 1 volt, 2 volt or 3 volt depending on the circuit condition. So this says that the the output voltage is always less than the V always less than the input voltage by VR when the diode is off. If the diode is on, the output voltage is 0. As you can see now, the output voltage is 0 when Vin is more than VR. So let us also see how does the waveform will look like. So now we have written this dotted line input sine wave having sufficient amplitude. So we have marked this line also, which is indicating a reference voltage VR, which is mentioned here, which is there in the circuit. Now we know that if the input voltage is more than VR, so this is the input voltage. If it is more than VR, output voltage is 0. As you can see here, the output voltage is 0. For input voltage less than VR, so during this condition and during this input voltage, this output voltage is always less than the input by VR. So you can see now this from here to here, the Vin is less than VR, so that's why output is less than the input by VR. So this height will be always equal to VR. If the input voltage exceeds VR, the output voltage is 0, and this continues till your input voltage goes less than VR. If it is less than VR, in the entire negative half cycle, output is less than the input by VR. So that's what is shown here. So this is the reference voltage VR. The output is always less than the input by VR. So in this way, we can analyze this clipping circuit and write its transfer characteristics and the corresponding output waveform if the input is a sinusoidal waveform. So this can be analyzed by writing two equivalent circuits and the expression for the output voltage, and we have to know under which condition for what input voltage does these two conditions or these two situations occur. So when input voltage is greater than VR, the diode is on. If it is less than VR, diode is off. So that's what is being written here. This is the demarcation line making your diode on and diode off. We shall see one more circuit. This is circuit number 2. So now you can see this diode. So now you can see this diode is getting a positive voltage. If the input voltage is 0, it is now forward biased. So let us see how does the equivalent circuit of this second clipping circuit looks if the diode is on. So we are writing the equivalent circuit when diode is on. Now we are replacing this diode by a short circuit here. Now this is V0. So V0 is equal to actually V in. This is not VR, this is V in. So whatever input voltage there will be available in the output. So V0 is equal to V in. So this will occur when V in is less than VR. If this input voltage is less than VR, so this voltage is always less than the P. If the voltage at the end point is less than P terminal, the diode is on. So that's why when the input voltage is less than VR, we won't have the diode conducting for the entire period. So let us see how does the equivalent circuit and the expression for the output voltage looks if the diode is off. Now this is the circuit diagram when the diode is off. So you can see now it is represented by open circuit. This is V0. So V0 is equal to VR. So this will occur, or the diode will turn off if this voltage at N becomes more than P. So we know that at P we have VR. The voltage at N exceeds VR, the diode is off. So that's what the condition here. So that will occur when Vin is greater than or equal to VR. Now we should see the transfer characteristics of the circuit. So these are transfer characteristics. So here also always the input voltage is on x-axis, the output is on y-axis. So we have divided this horizontal input voltage, so less than VR and minus less than VR and greater than VR. So because VR is the one which decides when does the diode turns on or turns off. Now you can see when the input voltage is anything more than VR, so that this is VR, anything more than VR, diode is off. If the input voltage is less than VR, diode is on. So when diode was on, so we're going to have the output voltage equal to input. So you can see now this output voltage which is exactly on the dotted line, meaning that output is equal to input. Output follows the input when diode is on. When diode is off, the output voltage is VR. Now you can see this is constant now. So for this voltage, this constant voltage will be VR. So that will occur when the input voltage is more than VR. So you can see now the output voltage is VR when the input exceeds VR voltage, which is the reference voltage. If the peak voltage of the input voltage is 10 volts, suppose if the VR is 2 volts, so if the input voltage exceeds anything more than 2 volts, output voltage will be remaining at 2 volts. Now in all these cases, we are assuming the VD on to be 0, that is the on diode voltage is 0 volts. So typically it will be 0.67 volts. So let us also have a look at how does the waveform look like if you apply a sine waveform. So this is the dotted line indicates the sine wave, which is the input voltage. Now you can see we have marked one more line which is corresponding to VR if the input voltage is less than VR. So this is the reference voltage. If the input voltage is less than VR, so as we saw here, the diode was on, the output was actually following the input. You can see this blue line follows the dotted line. So if the input voltage goes beyond VR, sorry, if the input voltage goes beyond VR, that is now the input voltage is going beyond VR here, the output is now constant. The output is constant because diode is off. So output is constant at VR. So this continues as long as the input voltage is more than VR. The input is again reducing. You can see now input is again reducing. When the input reduces, again diode turns on. So when the input is less than VR, so now it is turned on. When it is turned on, V0 is equal to Vin. So it is following the input voltage. Likewise, this continues for subsequent cycle. The only condition is that in this particular case, if the input voltage is less than VR, diode is on, meaning that in this particular circuit, output follows the input. If the diode is off, the output voltage is VR because the drop is 0 across the resistor. Whatever the voltage that is here will be available at V0. So output is equal to VR. So this will occur when this diode is reverse passed. So this diode will be get reverse passed if the voltage at the N is more than VR, because we know that if the N terminal voltage is more than the P terminal voltage, the diode turns off. So let us have a look at one more circuit. So have a look at this circuit. So we have two diodes now. So once we have more than two diodes, now there are four possible conditions. Okay, both the diodes on, only D1 on, D2 off, and D2 on, D1 off, and both can be off. So these are the four possible combination. Like okay, it can be 0 0 0 1 1 0 1 1. So let us write the equivalent circuits when one is on, the other is off. Now we have considered the D1 on and D2 off. So the equivalent circuits have been written. So we are replacing the diode on diode by a short circuit and off diode by an open circuit. So as we see here, the output voltage here happens to be the VR1. So that's why it is V0 is equal to VR1. So this condition will occur if the input voltage is more than VR1. So you can see now here the voltage at the N terminal of the diode D1 is plus VR. So if this diode has to turn on during the positive half cycle, the voltage at P type of the T1 should be more than this VR1. So that's why when the input voltage is more than VR1 during the positive half cycle, this diode D1 will conduct. So that's why this is true. So anything less than that, so the diode D1 is also off. So why this D2 is off means because D2 is already reverse pass. So as you can see here, the D2 is already reverse pass here. So now we'll have a look at this. So D2 is already reverse pass because for this P we have a negative. So during positive half cycle this will be negative here. Sorry, during positive half cycle to this N will be having a plus voltage which will further reverse bias this. So that's why this is off. We shall see in detail the working of this circuit in the next video.